So let's talk first about power. What is the power? In other words, what is the power that comes into the system, into the continuum medium, along its movement? Well, power is work per unit of time. So probably most of you know the meaning of work. Work as, some mechanical work, which is the work done by some force. When it's moved, it moves something. When I just lift this object, then I do some work because I do some force, and as a consequence, I move that force along a certain space, and typically the force times the space is what we call mechanical work. Well, there are other types of work. We'll talk about that. What is the difference of work and energy? Or what is the relationship of work and energy? Well, imagine that I have some work moving this continuum medium, this object. So I'm doing some force along time, and I'm moving the force along time, so that produces some work as a function of time per unit of time. And that is what we call power, okay? So in a unit of time, I do some work. That work per unit of time is what we call power, which in principle is a function of time, because it can vary along time. Okay, sometimes, not always, depending, that work per unit of time with the power can be expressed as the ratio of some energy per unit of time. Sometimes, not always. In those cases, in these cases in which that work per unit of time can be expressed as a variation of energy per unit of time, in other words, as a differential of energy with respect to time, then we can say that this work is related to a certain energy, such that the work per unit of time, the power, is equal to the differential of the energy with respect to time. But this operation, relating power as a differential of energy, is not always possible. That's very important, and we are going to deal with that. Well, so let's talk about power, and let's consider what are the ways that we can introduce work per unit of time, that is power, into the continuum medium. I have this continuum medium, and then it's moving. And why it's moving? Because I'm doing some forces on the continuum medium. My hand is transmitting some forces that makes this continuum medium move. So I'm entering through my hand moving and producing a certain displacement of the body. I am producing some work. And then I can consider what is this work per unit of time along this motion. This is what we call the mechanical power. The mechanical power is then the work per unit of time that is entered to the continuum medium due to external mechanical forces. Okay, so that's the concept. If I don't introduce any work, if I don't introduce any mechanical forces to this continuum medium, it doesn't move. Okay, so it moves because I'm doing something, which is my hand, and maybe the weight which is done remotely by the gravity, that is the responsible that during the movement of this body, then there is some work of these forces. My hand and also the gravity, which is producing some work as I move this object. Okay? So this is typically what we call the mechanical power. There are other ways to introduce power into continuum medium. Typically thermal. Well, there are even other additional ways, but we are only going to consider just this one, thermal power. Why? Because we can introduce heat into the continuum medium. If I had a lighter, I could just produce some heating on the continuum medium. I can burn it, and I'm introducing some heat per unit of time. That is what we call thermal power. So we are going to talk about two types of powers. Mechanical power, which is the work done by the external forces to the body a long time, period of time, and the thermal power, which is the heat that is entering into the body, to the continuum medium, a long time. Okay? So that these are words, as ever. We said words. Now we're trying to express these words in terms of mathematical expressions. Okay, so let's consider our classical potato, our classical continuum medium. What are the external forces that act on this continuum medium? Well, the body forces, you know, typically the gravity. What else? Well, the surface forces. For instance, my hand, when it's moving it. What is the work done by these external forces, the mechanical work per unit of time, that is the power? Well, let's do it step by step. Let's consider a particle. Let's isolate it here, which occupies a certain volume dV. So the mass of this particle is rho differential B. On this particle, there are some body forces acting in a certain direction. So the total force, these body forces are per unit of mass. If we multiply them by the mass, rho dV, then you think that is the force that is acting at time t on this particle, what occupies a differential, an infinitesimal differential volume. Okay, that is force. What is work? Well, work is force times distance. In a generalized way, the work of a certain force which is moved through a certain distance is the product, the dot product, is no scalar. So it's a dot product of the force times the displacement of the point of action of the force. Okay? So in that case, let's consider now an interval from t to t plus delta t. So the length of the interval is delta t. Okay? In this time, that particle moves from that position to this position, and let's consider dr as the displacement of the particle at this time. Okay? Okay, so what is the work that these body forces have done due to that at this interval, t to t plus delta t, which is the force, rho b dv times dr. So rho b dv times dr. But this is the force done on the total interval. But what is work per unit of time? Well, since the length of the interval of time is dt, I have to divide that by dt. So rho b dr over dt, differential of b, is the work done per unit of time, so the power of these body forces at this particle. But look, that dr over dt, which is equivalent to differential of r with respect to dt, is the velocity. The space which is just moved, the particle divided per unit of time, is what we call the velocity. So finally, the expression of the power, mechanical power, due to the body forces on this particle per unit of time is rho, the body forces, times the velocity times dv. Okay? Well, this is for one point, one particle. What about the work of all which is the mechanical work of all the particles on the body? Well, we have to sum, that is to make the integral of this term over the domain rho b. Okay, b. Well, are there any other forces acting on the continuum medium? Well, we just defined that we were going to consider some other ways of some of the actions, mechanical actions on the body, which are the boundary actions. The actions that I do when I just, put some forces on the boundary of the continuum medium. And they are characterized by what we call the traction vector, which is the force per unit of surface. Okay? So of course, when this body moves, those forces also move, so they do some mechanical work. What is the mechanical work? Well, let's first, step by step, consider a particle on the boundary. A particle which has a surface, or which acts on, is on the surface of differential surface. at times t. So the force, the surface force on this particle is t times differential of s, because t is the force per unit of surface. So if you multiply by the surface, I obtain the surface for this particle on the boundary. And then at time t plus delta t, that particle, imagine that it moves from here to here. So the work that is produced by this body force, by this surface force, at the interval t plus delta t, differential of t, is the force, t differential of s, times the distance, differential of r. But now, if I consider that this is done in an interval t plus delta t, so the length, the time in which this movement has taken place is delta t, differential of t, so now the power, the work per unit of time, is t dr ds divided by delta t, and dr over ds is the velocity, so finally is tv differential of s. So this is for one point of the surface. If I just sum for all the points of the surfaces, that would be the sum, that is the integral on the surface, so in the boundary dv, delta v, of t dot b differential of s. Look that this is in scalar. These are two vectors. Vectors dot product is a scalar, so that is in a scalar. So now we have expressed mathematically what is the mechanical work that I enter into the into the continuous medium as it moves in the space, and there are some external forces or some also internal forces acting on it. Okay? Well, now let's elaborate a little bit on this concept. Let's consider, for instance, this term here. This term here in the body. We can elaborate a little bit. Why? Well, first we know that the expression that relates the stresses with the attractions at the boundary is that one that we call the boundary condition for the stresses, or some words with some abuse of description, we call that equilibrium in the boundary. Okay? So the equilibrium in the boundary said that the attractions has to be equal to the product of the stresses at that point times the normal to the boundary. So we replace that. So, and we obtain this expression. And sigma b, we group that. And now, by doing this grouping here, we realize that we have an integral on the boundary of the domain, of something, a kernel. This kernel can be expressed as n dot something. And this suggests that I could use, if I was interested, since this domain is closed, since the boundary is a closed surface, then I could use, if I wanted, the divergence theorem. And the divergence theorem there said that this integral on the boundary can be expressed as an integral on the volume, replacing the normal times the nabla. And that's it. So I do that. So finally, this is the interval of that. And then I do this operation. This operation, conceptually, is applying these nabla derivatives of a product. And you know the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. So more or less, you have to do the operations by indices. But more or less, that can be proven that divergence of sigma b, or nabla times sigma b, is nabla times sigma times b, plus c nabla b plus sigma nabla b. Then what kind of operators play here? That comes from the initial word. But if you do that, in the book it's done, we can do that this equality applies. And this is the gradient of velocities. That's a vector that we introduced, the velocity gradient tensor. Okay? And we also saw that this velocity gradient tensor was, by convenience, decomposed into the sum of one symmetric tensor. So the symmetric part of the gradient of velocity is what we call the rate of strain tensor. And it's symmetric. And the skew symmetric part is what we call the spin tensor. Okay? That's something that we did. It's in our pocket of formulas. But now we see that by using that decomposition into here, sigma times L, the spatial gradient of the tensor, is then sigma double dot d plus sigma double dot b. But now sigma is symmetric. We have already proven, the last thing that we did in the previous lesson was prove that sigma is symmetric. And w is skew symmetric. And you know, whenever we have a double dot product, a double contraction of a symmetric tensor times a skew symmetric tensor, the result is always 0. So this term cancels. So finally, at the end of the day, I can cancel this term here, so the mechanical power by the body forces, by this term plus what remains of this term, which is the integral on the domain of the stresses times the rate of strain. Okay, so that's the operation. I go back to my expression and I replace this result into here. And that's what we have here. The mechanical power entering into the continuum medium, we're going to denote this PE. P entering, P mechanical power entering. Power entering, mechanical power entering as a function of T is the sum, as we said, of the mechanical power produced by the body forces plus the mechanical power produced by the tractions. And that has been split into these two parts. And now I realize that I have integrals that now are no integrals on the boundary, but they are integrals on the domain. Okay? So now I can group these integrals. So let me put this term and this term together, and this produces the divergence of sigma plus b times v, which is this term, plus rho b times v. So I group that, plus this term that remains here. And I remember that in my pocket I have a formula which is the balance of linear momentum whose pointwise expression, the counterpart at the point level, is that equation. Do you remember the equation that we gave, the name that we gave to this equation? It should start being sounding for you. It's the Cauchy equation. That's called the Cauchy equation. We also, that in engineers used to call that the equilibrium equation. And in fact, it's nothing else than the second Newton's law. Force, these are forces, equal mass per unit of volume, density, times this, because it's acceleration. Force equal mass times acceleration. So that's something that it's always fulfilled. So now I replace that, and I replace that this is rho dv dvt, so I have replaced this term in here, and I have this term. And now I also realize that dv dt times v can be expressed as the differential with respect to time of 1/2 of b times v. Do the expression. It's 1/2 of b times dv plus 1/2 of dv times v. But since the product is the same, they can be inverted and they will obtain that. So that's true. And b times v, what is a product, a vector times itself? That product times, scalar product times itself. The norm of the vector square. Okay? So that can be expressed at the end as rho differential with respect to time of what? 1/2 of the velocity. Look, this is not a ball, this is a scalar. That means the modulus of the velocity square. Okay? So, well, these operations, that in my opinion, are nice to do because it shows the power of combining physics and continuum mechanics. Finally, we obtain that expression that says that the mechanical power entering into the domain is that term plus that term. And now, I also use another formula of our pocket. You remember that we said, well, if you want to obtain the material derivative of an integral, and the kernel of the integral is rho times something, you just have to do the integral on the domain of rho times the derivative of the something. Look, let's consider that this is the something. So this can be expressed like that. Differential of that of this which is rho times something, is equal to the integral of rho times differential of something. That this is now re-expressed in that way. Well, I did some work, and now I'm able to understand physically what is the power that I enter, the mechanical work per unit of time, that I enter into the continuum medium, in what, physically, in what issues is it spent? And now I'm going to do that. Look, I've arrived at the mechanical power, which had this expression, after some operations and accounting for some other principles that I've derived before, can be expressed like that. Look, the integral of volume of 1/2 of rho b squared being the modulus of the velocity square. Is that sounding to you to something that you know from mechanics? What is the kinetic energy of one mass? 1/2 of mass times velocity square. If the mass is infinitesimal, that would be 1/2 of mass rho differential of b times b squared. If now, so that the kernel is the kinetic energy of one particle. If we sum for all particles, this term is then the kinetic energy of all particles in the continuum medium. So all particles here, when I introduce some mechanical power, some external forces, the gravity, even if I don't have any external forces, there is an action which is the gravity forces that produces some movement of the body. So that mechanical power, on one hand, is again a balance. That is the mechanical power that I enter into the continuum medium. And now at the right hand side, we have what are the consequences of this mechanical power? What are the consequences? In what this mechanical power is spent off? And the first part is that, well, that is a variation per unit of time of the kinetic energy. So that means that whenever I introduce some external work on a continuum medium, there is a variation of the kinetic energy. Look, this is that. I release that, so the actions are the gravity forces, the body forces. What happens with that? It increases the kinetic energy. It starts moving, increasing the velocity. Okay? Or even if I do that is at rest, and now I increase my external forces and I make it move. So now I'm producing some increase of the kinetic energy. So that says that the mechanical power I'm entering into the body is spent into a variation increase of the kinetic energy. Look, that can vary a long time. For instance, if I release my hand here, that the kinetic energy is increased because the velocity increases. But if I now grasp again the body, then I'm introducing some external forces and I make the kinetic energy to diminish to zero. That's what I'm doing here, right? So I've introduced a long time some external power by means of forces, gravity forces, or my hand, external forces, and the result is that there has been a variation of the kinetic energy from zero to something and then again to zero. Okay? And look, that's something that you should know already. Probably you have already seen that. Because that is what is called the theorem of the expended power. In Catalan, we call that Teorema de las fuerzas vivas. In Spanish, Teorema de las fuerzas vivas. That's something that it's part of the mechanics, rigid body mechanics lessons that says, yes, whenever you have a system of particles or rigid body and you introduce some mechanical energy into it, the result is that the body changes its kinetic energy. And the rate of change is equal to the power. But here, we are dealing with something else than rigid bodies. Look, I could consider that body, and I could do that. That body is deformable. So I can introduce external power, and of course there are some variation of the total kinetic energy. But it looks like there is something else. I'm introducing new stresses into the body. I'm producing strain into the body, right? And this is what this theorem says. Part of the mechanical power is spent in variation of the kinetic energy. But if the body is deformable, it's flexible, so to speak. Well, flexible, it's a little abuse. It's deformable. There is another part which is devoted to produce that. That is what that is stresses. Time, rate of strain. So stresses time strains, which is work per unit of time. That is what is called the stress power, the work per unit of time of the stresses. If I introduce some stresses into a particle and this produces some strain, the work is the stresses times strain. And the work per unit of time is the stresses times strain per unit of time. The strain per unit of time is D. Okay? So that is the stress power. And then the famous theorem of the expanded mechanical power, which in rigid body mechanics only has this first term, now it says the following. The mechanical power that I introduce into my body is spent in two things. First, to vary the kinetic energy, as it happened in rigid body mechanics. And in our case, on top of that, there is one part of this mechanical power that is devoted to produce a stress power. That is work, internal work of the stresses. Okay? If the body is rigid, then there is no deformation, there is no strain. So that this term is negligible in rigid bodies. So now this amount is discarded. But now we are not doing to that because we want to deal with deformable bodies. So that, and again, this is a balance equation. In one side of the balance, I have I enter some power, and at the right-hand side of the balance, I have some consequences, which is the variation of the kinetic energy and the creation or the diminution of stress power. Look, that I call that energy. Why is this energy? Because, well, the power, look, the differential of the energy provides the part of the kinetic power, okay? So in that case, if I consider that term here, I can talk about kinetic energy. But here, that term, and I'm going back to that in a few lessons, a few slides, then that term is not the differential of something. So I'm not talking about, for instance, deformation energy. I'm not talking yet about deformation energy. This is not the differential of anything. The stress power it exists, but is not the differential of nothing. So in principle, I cannot talk about any strain energy. I will, but not now. Not from the ingredients I have so far. And then the stress power can be defined then as that part of the entering power which is not spent in changing the kinetic energy. Okay? You have these concepts already consolidated? Okay. So now let's consider another way of introducing power into my body, into the body I'm dealing with. So imagine the continuum body, and imagine that I enter, by some reasons, some heat into it. That heat entering into the body per unit of time is what we call the thermal power. And it's another way to introduce power that is work, but that time in terms of heat per unit of time. So we are going to consider two ways of introducing heat into the continuum medium. Well, remember that I said that we could consider that every particle of the continuum medium as having properties and saving or keeping those properties into a pack that every particle carries. Okay, now imagine that heat. Now we are focusing our attention on heat. So let's look at the heat of every particle. Well, how this heat can be increased? Well, it can be increased by two reasons. First, because I'm exchanging my heat with other particles. I'm sending my heat to other particles. My heat, I'm sending some heat to you, or you are sending some heat to me, some heat to me. That is a way of entering heat, by non-convective heat. Okay, that's the way we said, because that is independent of the mass transport. Even if I am at rest, then I can exchange heat with others. And then, of course, if I send in this way, non-convective way, if I send heat to other particles, I'm losing, every particle is losing part of the heat. Well, this heat can be sent to particles of the interior of the body, but it can be also sent to particles at the exterior of the body. Okay? So that part that goes to particles at the exterior of the body is a loss for the body, of the heat for the body. Due to what? To non-convective transport. So how do I evaluate that? Well, I said that there is some way, there are some other scientific branches, scientific theories, that evaluate what is the amount of heat that every particle sends to others in terms of what? In terms of what is called the heat conduction flux vector. When the non-convective flux, the non-convective transport of heat, in the case of heat, is called conduction. I told you. In the case of other diffusion, it's called other words. Okay? But in the case that, then we can define the heat conduction flux vector as that vector so that integrated on the boundary of the domain and integrated, multiplied by the normal, produces a scalar whose integration, the sum for all the boundaries, provides the income heat conduction vector. So if it's positive, that means that there is a loss, the outgoing flux conduction vector. So if the product is negative, that means that the body is losing. Okay? So what is the amount of heat that the body is gaining minus what is losing? So finally, that expression, so we can quantify the amount of the total amount of flux of heat that enters per unit of time into the body for non-convective reasons, for non-convective transport, through this assumed known heat conduction vector and this integral. Okay, so this result is the incoming heat per unit of time due to conduction. Okay? Okay. But is there any other way to introduce heat into my body? Of course, I told you. As a particle, I could have internal sources of heat inside me. Typically, in concrete, the hardening reaction of concrete, okay? Which is exothermic. So there is heat which is produced inside the particle. How do we characterize this amount of heat? By what is called a function, scalar function, which is, of course, as the heat conduction function of space and time, which is called the specific internal heat production term. So imagine that I know that. So I can quantify that. I could study what type of concrete I am, a particle of concrete I am, what is the amount of gel that I have, the amount of water, and the amount of cement. So I can just, in terms of that, obtain through a formula, to some experiments, what is the amount of heat that produces the reaction per unit of time in every particle. And per unit of mass. If I multiply by the mass, obtain the heat produced interiorly per unit of volume. If I sum, that is, I integrate on the volume, I obtain all the heat produced by that. Maybe there are other reasons for which heat can enter into the body, but let's stop here and consider that these are all the reasons that we are going to consider for entering heat per unit of time, that is entering thermal power into the boundary. So finally, the amount of heat that enters into the body, the continuum medium, per unit of time, which is going to denote Q entering, T of course, is that part that comes from the internal sources of heat, plus this part, plus minus that part that comes from the conduction, heat conduction, exchange with the exterior of the domain. And now I also the same operation as ever, you know. I've set the integral on the domain, on the boundary of a closed domain which involves in the kernel some n, the normal. So I just invert that because this is a scalar product of two vectors that can be inverted, can be transposed, so it's n times q. And now I apply the divergence theorem. I replace n by the divergence, and I replace the integration on the boundary by the integration on the volume. So finally, I obtain this term, and now I can join these two terms in a unique volume integral, which is rho r minus divergence of q. So what is divergence, the meaning of divergence of q? The counterpart at particle level of that of the heat which is loss due to conduction, to exchange by conduction with exterior. Okay? At the local level, it's clear that it's that. At the global level, at the local level, that term is the counterpart of that. Okay. So let's assume that these are data, right? We should know in order to deal with that. What is the expression, the mathematical expression at every point, at every time of the conduction flux vector, and then also the internal sources expression. Okay. So now we can sum. We have that at this body, for this body, there are two reasons for entering heat, for entering power, work per unit of time. Mechanical reason and thermal reasons. And we know that mechanical reasons, the mechanical power, is equal to that part here. And we also have seen that the heat power is equal to these two terms here, okay? Which can be expressed in that way or alternative in that way, okay? That is the total power, okay? Again, it's a balance. That means that, look, the total power that I enter into this body, now accounting also for thermal power, is spent in what? In variation of the kinetic energy, in producing some deformation work, the stress power, which is here, in increasing increasing the heat due to the sources, internal sources, and losing or gaining some heat due to conduction with the exterior. Okay?